So we've talked about just what a network graph is. So we're going to do a very basic network, okay? Our network is just going to be 4. And I'm going to reuse this network over and over, okay? And let's say that our network is fully connected. And actually, for this purposes, I just realized I do have to add a 5th one just to make. Yeah, we'll just go with that one. Yeah, that's good. So we have this, and then we also, our network also is weighted, okay? And this is the network that we're going to use. So here we have a weighted network. It's undirected, so we can go and flow to and from. There's no limitations, and I can go from each direction. There is some, of course, in some of your homeworks where you have a issue where you can't. But here we have this. So I'm going to make a copy of this because we are going to use the same type of one over and over. So just to get a little bit of notes. So this will be example used for class. Oops. Example weighted network for class. So some definitions that will be helpful for you to know in terms of your exposure. If you ever take a computer science course or an advanced computer science course, this idea that we've been doing right here with graph theory is something that's actually super, super important. And so therefore the vocabulary becomes important. The first thing that we want to talk about, so traveling along the network. Some vocabulary. And the first one is called a walk. Okay? So a walk is a sequence of vertices and edges I want to say any sequence of vertices and edges that's it. Any sequence of vertices and edges. And it should be noticed that vertex can be repeated and edge can be repeated. So everything we're going to be doing today is technically considered a walk. All right, so we're going to walk along our network. So everything we're going to do is a walk. Okay. So, for example, a walk could be A, B, D, A, C. Oh, and I forgot to label this bottom one as E, sorry. So this can be considered a walk right here. This is the notation we're going to use. You can use arrows to do these, but we're going from A to B to D. So visually what I'm saying is we're at A, we go to B, we go to D, we go back to A, and we end at C. Okay. Now, every walk also has a cost. So cost, the sum of the weights from the walk. So what would be the weight? What would be the cost of this walk? And now, when we say the cost, it could literally be how much money it is. Maybe it's $2 to go from A to B, $3 to go from B to D, $5. You can think about it as you can multiply these by 10. It could be like taking the train and it's $20, $30, $50, $100. This could represent you can put a lot of different applications at what the cost represents. Most of the time we talk about minutes. It could be how long it takes. How many hours does it take to travel from A to B? It takes 2 hours. From B to D, it takes 3 hours. From A to D, it takes 5 hours. And the longest travel, of course, is A to C. Maybe there's easier access. You can directly fly in. If you're talking about a major city, for example, A and B are could be a major airport city like Boston, and B is like New York, right? So you have a direct connection, whereas C might not fly directly into A, so you have to fly, but then you also have to take some the car and all that kind of stuff. So it takes a lot longer to travel to C directly from A. Because you have to do a lot other things that are involved. So there's a lot of different parts. So what would be the sum of this one? Well, the cost would equal 2 plus 3 plus 5. It's 2, 3, 5, and 10. Plus 10, which would be 20.
That's it?
For that one, yeah. That's it for that part. Right, for that.
And it's always, I just add in?
Yes. That's all the cost is going to be.
So it can be like multiplying or?
No, there's no multiplying in networks. So we're always just adding because we're walking along it. So it's how much does it cost to get from vertex A to vertex B? It costs 2. And so if we're going to walk from A to B, from A to B to D, back to A, and end at C, it'll cost us 20. Okay? 2.
Mister, I have a question.
Yes.
When adding them all together, does it matter where you put the numbers, or do they have to follow a specific pattern, or can they just be random?
They're not random at all. It follows the whatever network you're given. So this says I'm starting at A. So another notation that you might see is A arrow B, arrow D, arrow A, and arrow C. These are, both of them are okay in terms of your our notations. When I'm going to ask you to find different particular walks. So I just left it at using, you can just do comma, 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 telling me that this is how we're walking along. Because I felt the arrows were going to be a little bit more difficult for you to try to type into the Google document. Does that make sense?
Yeah, it makes sense.
Okay. So, walk. Everything is a walk. Second thing, let's get into a little bit more specific. We can say what's called an open walk. Okay? An open walk is a walk where the starting vertex or starting vertex differs from the ending vertex. So is our example above, is that an open walk? Yes or no?
Yes.
Yes. It is actually an open walk. Why? Can you clarify why that the above example is an open walk?
I mean, nothing's stopping it.
So why is the above an open walk?
I don't see why it can't.
Why is this an open walk?
Because it follows a pattern. Oh, but
Because it starts at A and ends on C, which is not A.
also, if it doesn't end in the same place, it doesn't end in the same place.
Mm-hmm.
It's open.
Correct. And if it starts in the same place, we have what's called a closed walk. So a closed walk is a walk where we start and end at the same vertex. So basically here, like think of a round trip. So if you do a round trip, like you start in Boston and you travel around and then you come back home in the end, right? So you end your trip back home. That's a closed walk. So for example, A to B to D and then A. So if I were to start at A, go to B, come down to D, and end back at A, that would be a closed walk because I end where I started. Okay, I end where I started. Now, don't worry too much about these vocabulary words. You're like, wow, okay, path. A walk, an open walk, closed walk. I'm actually not going to be, like I said, I'm not going to be asking you these ones on your homework. Everything's a walk. Walks, it don't matter if we cover the same vertex or even the same edge. It does not matter. Four, a circuit. Those of you who follow physics, a circuit, and this is exactly kind of what a circuit is. Or sorry, I'm actually missing one. Yeah. Sorry. Before we get to circuit, I need to do the next one. Trail. A trail is a walk where the vertex is not repeated. sorry, edge is where the edge is not repeated. So think about if you're walking on a trail, you go for a hike, right? The idea is that you can, if you've ever gone hiking, you might crisscross and you might actually come back and meet to the same point, but you never walk along the same path, right? That part that you walk on. So you might end up coming back. So the above example on top, we would consider that a trail. So A, B, D, A, C is a trail. Because although we do go back to A, my edges are AB, BD, DA, and AC. So I never actually walk across the same path over again. So I do touch the same vertice, but I do not touch the same edge. I do not walk across the same edge. Every edge is different. Five, a circuit. A circuit is simply a closed trail. So edges not repeated and end where we start. So the example that I wrote above about A to B to D back to A is a circuit. We start at A, we go along this edge right here, we go to B, we go along this edge right here, we go to D, and then we go along this edge right here, and we end back. It's a circuit. We closed it. We closed the trail, or we closed the circuit, because all circuits are closed. You have to be able to wrap around and get back. And if you think about electricity, how electricity flows, you can't have the electricity flow back onto itself. So a circuit is, we can't walk across the same edge, because that would be kind of like, bad in terms of electricity. So we're just like do, and then it's closed. So a circuit is technically a closed trail. Like I said, if you don't, a lot of this right here, I just want to give you this vocabulary. We're not going to utilize all of them. It's this next one. This is the one that we're going to use. All right. This is the one that I really want you to make sure everybody has, because it's what your homework is on. It's a path. All right, we're going to focus on a path. A path is a walk / trail in which no vertex or edge is repeated. So think of it as traveling different cities one way. So we want to get, when you plug into, and this is the idea behind Google Maps, right? You're trying to get to a certain location, but you might have to make certain stops. You're going to go to here, then you're going to go to here, and then you're going to end at your final location. A path is going to, you're going to end somewhere differently. All right. Well, technically you don't have to. Technically a path can be closed. it would still be considered a path if you come back home. So whenever you do Google directions, basically what you're doing is a path. And that's why I'm going to focus on this one right here. So the above examples are not paths because we came back and we touched the same vertex. So A to B to D to A is not a path because we cannot repeat. So this is the one that you're going to do. So for example, let's name multiple paths from A to E. All right, so this is kind of what I'm asking you. Well, let's name all. Let's find all. Name all, find, name, find. Name all paths from A to E. And this is what I've asked you to do on your homework. So once again, we are utilizing the same image. This is what we have right here. And we want to get from A to E. We want to get from A, so this is where we're starting, right here. And this is where we want to get to, right there. And in your homework, I'm going to ask you to do this. I'm going to give you a starting point. No, you do not. You do not need to use all of them. You do not need to do, and find the cost. All right. So let's do this. So for my notation, I'm gonna say this. This is my first path. Can someone tell me how to get from A to E without repeating a vertex, without repeating an edge? I'm always gonna start at A. So A, then B, then D. Yeah. This is what Christine said. Then C, then E. Yeah. That's a long way. She decided to go through all of her trips. She touched every city. So if these represented cities, she visited every city and she finally gets to A. So this is one of the examples. So she started at A, she went to B, then to D, then back to C, then ended at E. And that was the goal. The goal was to get from here to here. Now this is just one possible path. What was the cost of this path? Oh, it's 2 plus 3 plus 4 plus 1, which is 10. Okay. Can someone give me another path? Path 2. This is going to be our second path right here.
A, C, E.
A, C, E. That's pretty much the most direct path, right? It seems to be like the least amount of edges. I only cover 2. It's only two trips, right? That is a path. I go from A to C to E. So boom, I'm just getting from A, trying to go the most direct way possible. And what is the cost of this path?
11.
10 plus 1, which is 11. So as it turns out, while this path seems shorter, it's actually more expensive. So it was cheaper for us to go from A to B to D, then to C, then to E. Can I get another one?
A, D, E.
A, D, and then E. Perfect. That has a cost. I'm not going to go through all the cost. I just want to kind of finish these off. Can I get another path?
A, B, D, E.
A, B, D, E is indeed another path. A, B, D, E. The previous one was A, D, E. These are different paths that I can take and can walk. Now it turns out that this path and this path actually both cost 8. So I can go here to here and here, here, here. Both of these would cost 8. And so I'm also going to note that the minimum cost turns out to be 8. And that can be done by 2 different ways. So that could have been done by, so this one has a cost equal to 8. This one has a cost equal to 8. So both of these paths are what we would consider the minimum cost. And that's kind of what happens. Now, you can see that there's not a lot of options here. Well, there's only 5 different cities or 5 vertexes, all right? So the amount of possibilities of travel, the amount of edges that we could travel about isn't really that big at 5, okay? So it's not really, really big. So we can actually crunch the numbers to see all of the options, all right? However, what happens in real life is that there is a cost to go directly from B to D. There is a cost to go directly from over here as well. So if I were to add in these ones right here, and then if I add in this one, and so that we can go from everyone, now the number of possibilities and paths grows what we refer to as exponentially. And in the real world, the amount of different possibilities becomes so large that if we were to try to do what we're trying to do right here, we would be doing this forever, because there's possibly a million, and it even gets to 1 billion and 1 trillion different possibilities really fast. The amount of possibilities goes really, really fast, and it blows up. There are computers that we utilize to do this, and even computers can do it fast enough, and a computer can't even figure out every possibility without taking hours. So this is why Google made so much money. Google is such a valuable company because they were one of the very first companies, computer companies, that figured out a way to answer the question, what is the minimal cost to get from A to E possible? They did it well, and what they happened is they did it better than everybody else that came before them. They were able to say, if I start here and I want to end here, how can I do that as best as possible? This is one of the reasons why. All right. So when you search for something, when you do a Google search and you're searching, they want you to find what is what is best and most applicable to you. So that one of the main things was searches, and so you can flip into the opposite. So let's say these were ratings, right? They want to make sure that they list all of the ratings. So when you search for something on Google, your top search comes up, and we can get into how they're doing their searches. It becomes rather, it's a pretty cool course and idea to do as well. It's called algorithms. I think I feel it push a little bit too much on the work that we would do in this course. But that's one of the things they did. And when we talk about Google Maps, this is what Google Maps does. They determine the cost of every single street, and this is live data. So when there's a traffic jam, everything keeps changing. So they can keep data and update their data over and over and still produce what is basically the shortest path, the lowest minimum cost possible for you. Now, is it the lowest? The answer is no. When you type in a Google Maps, say I want to get from here to here, it doesn't technically give you the minimal cost, but it gives you pretty much what is good. Because if you've ever used Waze, people will go, oh, Waze is so much better because Waze will get you there faster. Well, Waze's focus is like, it doesn't matter if they turn you down 20, 30 streets. You go through, if you've ever taken a trip or you ever do and you use like Waze, you might make like 30 turns, You're going to go down this side street, then this side street, then this side street, then this side street, and you end up saving like 1 minute in the end. Cost lowers by one cost. Where Google Maps might not say, you know what, we're not going to make you take all of those turns. We're going to get you there pretty much the minimum time. And 1 minute, it's not that much of a difference. We're just not going to have you make 30 turns. You might end up having to make 3 different turns. And most people would prefer those 3 turns rather than the 30. And some people just, everywhere I want to go there the fastest. So that's kind of the difference. So this is what you're going to be doing on your homework. Before I go on that one, I want to say the last possible thing, the last one in terms of vocabulary, and we're not covering this, it's called a cycle. And all a cycle is a closed path. So it's where you end, where you start. You don't repeat anything, and technically, yes, you're repeating the vertice because that's where you end, but you end where you start. So this is a round trip. All right, so all I want you to do is finding the paths. So how many possible paths are there? In the first homework example, and let me pull up the homework now. So in your homework, oh, that should say Thursday right there. Let me update that real quick. Oh, I gotta do it on my other computer. I'll change it to Thursday. In the homework, problem 1, I've told you exactly how many paths there are. All right. In the first problem, I've told you exactly how many paths there are. I've told you that there are 6 different paths. So I've actually told you exactly how many there are. There are 6 of them. I want you to get from 0 to 2. I want you to get from that vertex 0 all the way to vertex 2. And there are 6 different possibilities. I'm telling you explicitly, there are 6 different possibilities. Find all 6. Okay? In the second one, there's not 6 possibilities. Okay? There are not 6. There's actually a lot less. I think, if I'm correct, there's 1, 2, there's 1. Huh? I think there's only 1. Huh. Maybe I'm wrong. There might be there's only actually 1 path on problem 2, for example. So I want you to, there's no other way. So these are direct. You can't go again. You have to follow the arrows. So in problem 2, I'll verbally state this out. There's only 1 possible path from getting from A to B. Does everybody see how there's 1 path? Anybody disagree with me on problem 2 that there's more than 1 path?
No.
So the only path possible to get from A to B is for starting at E, sorry, from E to B. Start at E, go to A, go to C, go to B. So there's only 1 path possible. Because you can't go from A to B because it's a one-way. Okay? And then we have 3. You want to start at A and you want to get to E. Now, on this example, there is more than 1 path. I will not tell you how many paths there are, but there's more than 1. Okay? Let's just say that there's more than 1 and less than 6. All right? It shouldn't be too hard. Problems 2 and problem 3 are actually a lot easier with the directeds. I explicitly told you how many paths there are in the first problem just to help. And also I want you to note that I need you to highlight whichever one cost the least. So after you find the path, highlight them all and then add up the cost. That's what you're doing for your homework. If you have any additional questions, I'm still here. Beyond that, class lesson for today is done.